In this paper, we present TANDEM3D, active tactile exploration for 3D object recognition. We studied tactile recognition of 3D objects, where one object must be identified out of a set of known objects based only on touch feedback. We mount the disco tactile finger with all-around sensing coverage on the UR5 robotic arm. The unknown object is placed in the workspace with random position and rotation along the z-axis. The robot interacts with the object and needs to identify it by collecting a sequence of contact locations and normals. We select 10 objects from the YCB dataset. As shown in these 4 examples, with such few contacts, it's almost impossible even for humans to identify these objects correctly. However, TANDEM3D can recognize these 3D objects with very few actions. We address a number of challenges to achieve this. Tactile sensing is fundamentally an active sensing modality, and touch sensors provide local and sparse information. As a result, the guidance for tactile exploration is extremely important. There's no straightforward heuristic for exploring 3D objects. For example, edge following is an efficient heuristic for 2D shapes. However, at any point on the surface of a 3D object, there are an infinite number of ways to follow the edge. We need more advanced encoding techniques to generate 3D object representations. Simple formats such as occupancy grids or voxel grids throw away rich contact information such as precise contact locations. Also, their size grows with the size of the workspace, which is not memory efficient. Finally, more dexterous action space is required to move flexibly and freely on a 3D surface. We allow the finger to move in 6 action space. At each time step, the robot picks one of XYZ, row pitch yaw, and can either increase or decrease for a small step. In total, there are 12 discrete actions. Now we discuss our proposed architecture in detail. We identify 3 key components that are learned for our task. The encoder computes 3D representations from the sequence of sparse tactile information. The discriminator looks at this representation and predicts the identity of this object. The explorer generates the next action for the robot to take in order to collect more information. Specifically, the tactile finger interacts with the object and collects a sequence of contact locations and normals. Our proposed encoder first rearranges the collected sequence of contact locations and normals into a point cloud. These point clouds are then passed through 2.net++ based networks to generate the 3D object representations of dimension 1024. We choose the .NET++ architecture because it's permutation invariant and can handle different length of points. This 3D representation is then passed to the discriminator to predict the identity of the object and the confidence value. If the confidence is greater than the predefined threshold, the episode is terminated and the final prediction is produced. Otherwise, the 3D representation is fed into the explorer and the explorer will compute the next action. Despite that we have distinct decision-making and exploration policy modules, their training is highly interleaved. The discriminator is modeled as a CNN and trained with supervised learning, while the explorer is modeled as an RL agent and trained with PPO. During the co-training process, the discriminator provides termination signals to the explorer, and a sparse reward of 1 is given if the exploration is terminated by the discriminator. On the other hand, the explorer collects a dataset of point clouds and corresponding identities for the discriminator. In the co-training process, each component affects the other, improves the other, co-evolves, and then converges. Our method is trained entirely in simulation with Pivot Simulator, using different sensor noises, and then zero-shot transfer to real robot. Now we show a demonstration of our method on the real robot. The object is placed randomly in the workspace. We visualize the predicted distribution over 10 objects by the discriminator and the collected point cloud information. Our finger moves in 6 action space for efficient exploration on 3D surfaces. It reacts to previous observations and moves to the most discriminative area. In this case, it is the picture handle. Through a swing motion utilizing the full sensing coverage of the finger, the explorer gets a discriminative contact on the handle. This is top-down view of the swing motion. Through another swing motion, the discriminator quickly converges to the true identity of this object. It only takes 37 actions to recognize this picture base. We show another example on the power drill. The finger moves up from beneath the drill to get a discriminative contact. This time it only takes 9 actions. This example is on the Bleach cleanser. A distinct shape of this object is the curved recess on the upper body. Based on a sequence of past contacts, the finger continues moving up. It initially gets confused between Bleach cleanser and cracker box because both are tall objects and hard to distinguish. It decides to go to the back of this object and eventually contact the discriminative area to tell it apart from the cracker box. For the example on bow, our method immediately recognizes it after a contact on the bow rim, with only 9 actions. TANDEM3D outperforms a variety of learning-based and heuristic-based baselines in terms of both accuracy and the number of actions. It also generalizes much better to larger sensor noise beyond training. See our paper for details on these results. Thanks for watching.